No one believed that an entirely different kind of human could still be hidden beneath the ground of South Africa. Then, in 2013, everything changed. By pure chance, researchers uncovered a handful of bones belonging to humans no one had ever known existed. And the most unsettling part was this: the story of human evolution may never have been as simple as we once believed. This is the story of Homo Naledi. It all began as a routine expedition when cave explorers Rick Hunter and Stephen Tucker surveyed the Rising Star cave system in South Africa's Cradle of Humankind, a UNESCO World Heritage Site renowned for preserving countless fossils of early human ancestors. Inside a chamber that had received almost no scientific attention, they came across several fragments of bone. At first glance, they appeared no different from the many animal fossils that had already been discovered throughout the region. But when the photographs were sent to paleoanthropologist Lee Berger at the University of the Witwatersrand, he immediately realized they could represent something entirely different. The greatest challenge, however, was finding a way to reach them. To access the fossil chamber, the research team had to navigate a vast underground maze stretching hundreds of feet. The journey began with a steep rock ridge known as Dragon's Back, followed by the infamous passage called Superman's Crawl. Yet neither of these proved to be the final obstacle. Ahead lay a nearly vertical rock fissure, whose narrowest point measured only about 7 to 8 inches across, roughly the width of a sheet of printer paper laid on its side. A single deep breath or carrying too much equipment could leave someone trapped inside the mountain. After squeezing through the crack, the archaeologists still had to descend nearly 40 feet before reaching the Naledi chamber, a cavern that had remained in complete darkness for hundreds of thousands of years.
The man is hopelessly insane.
The challenge forced Lee Berger to search for archaeologists who possessed not only scientific expertise, but also climbing skills, caving experience, and bodies small enough to fit through a gap only a few inches wide. In the end, 6 female scientists from several countries were selected. They soon became known around the world as the underground astronauts. Then, as the beams from their headlamps swept across the chamber, they revealed a sight that left the entire team almost speechless. Beneath the layers of sediment lay not just a handful of scattered bones, but thousands of fossils spread across the cave floor. After years of excavation, researchers recovered more than 2,000 fossil specimens representing at least 28 individuals of Homo Naledi. What made the collection extraordinary was that it preserved nearly the entire life cycle of a population. From infants and young children to adolescents, fully grown adults, and the elderly. In paleoanthropology, discovering even a single nearly complete skull is considered exceptionally rare. Yet at Naledi, scientists were able to study an entire community spanning every stage of life, allowing them to reconstruct body structure, patterns of growth, and differences between individuals with a level of precision that very few archaeological sites anywhere in the world can provide. To this day, it remains one of the richest collections of ancient human fossils ever discovered in Africa. The more scientists studied the evidence, the more they realized that the simplest explanation seemed to be the hardest one to accept. The first hypothesis was that the chamber was nothing more than a natural trap. Even today, sinkholes and deep caves exist where animals accidentally fall in and die because they cannot escape. Over time, the remains of many individuals accumulate, creating what scientists call fossil graveyards. But when geologists analyzed the structure of the Rising Star cave system, they found that more than 99% of the fossils in the Naledi chamber belong to a single species, Homo Naledi. Homo Naledi may have deliberately placed their dead inside the cave. This hypothesis was first proposed by Lee Berger and his colleagues in their earliest publications, and it remains the most controversial aspect of the discovery to this day. They may simply have carried the deceased to a separate location rather than leaving the bodies where they lived. What makes this even more fascinating is that the scientific community itself remains highly cautious about this hypothesis. Many experts argue that the current evidence is still insufficient to conclude that Homo Naledi intentionally disposed of their dead. And it is precisely that uncertainty that has made Homo Naledi one of the most compelling mysteries in the study of human evolution. But if Homo Naledi truly ventured deep into the cave system time and again, they would have had to travel hundreds of feet through passages completely devoid of natural light. So what allowed them to find their way? Had they learned to control fire, or is this simply another coincidence that we have yet to fully understand? That very question opens the most controversial chapter in the entire story of Homo Naledi, where traces of fire, engravings on cave walls, and mysterious structures hidden deep within the cavern begin to challenge every limit we have ever placed on a small-brained human species. First came the question of fire. It was far more than a source of warmth or a way to cook food. Inside a cave system like Rising Star, fire would have been almost essential for seeing the way forward. Just a few steps beyond the entrance, all natural light disappears. Berger and his colleagues argue that fragments of charcoal, soot deposits on certain rock surfaces, and areas showing evidence of past heating inside the cave may indicate that Homo Naledi used fire for illumination. To date, however, no direct evidence has shown that Homo Naledi knew how to make fire in the way Homo sapiens later did. Even whether they used fire regularly, or only under certain circumstances, remains unresolved. But fire was not the most astonishing discovery. In several areas of the Rising Star cave system, the research team also reported geometric engravings carved into the dolomite walls. These include intersecting straight lines, X-shaped figures, square-like patterns, and repeating motifs. According to Berger, the markings bear the characteristics of repeated cuts made by a sharp object rather than random fractures produced by geological processes. If that interpretation is correct, Homo Naledi may have engaged in a form of symbolic behavior more than 240,000 to 330,000 years ago. This is where the debate becomes most intense. Many archaeologists and geologists argue that before describing the engravings as art or symbols, researchers must first demonstrate that the markings are truly the same age as Homo naledi, and completely rule out the possibility that they were created in modern times. The same controversy surrounds the hypothesis involving shallow pits and stone structures that Berger's team suggests may have been connected to the handling of the dead. Critics point out that these features could also have formed through natural geological processes. That does not necessarily mean Berger is wrong. It reflects the way science works. Throughout the history of archaeology, many discoveries that initially captured worldwide attention were later disproven, while other hypotheses first met with skepticism eventually became the foundation of modern science. And amid all these debates, researchers needed only to examine the skeleton of Homo naledi itself to realize that nearly every part of its body seemed to tell a different story. Its skull resembled that of very ancient ancestors, yet its feet looked remarkably similar to those of modern humans. Could it be that Homo naledi challenges not only our understanding of behavior, but also the very way we understand the evolution of the human body itself? Normally, experts can examine a fossil skeleton and determine with remarkable accuracy where it belongs on the evolutionary tree. But with Homo naledi, that rule almost completely breaks down. For this reason, Homo naledi is considered one of the clearest examples of mosaic evolution, a process in which different parts of the body do not evolve at the same time, but instead change independently under different selective pressures. The first impression comes from the head. The skull of Homo naledi is relatively low, with a sloping forehead and a face that still retains many primitive features. Its brain measured only about 28 to 37 cubic inches, less than half the modern human average of approximately 79 to 85 cubic inches. Judging by the skull alone, many paleoanthropologists would associate it with Homo habilis, or other very early members of the genus Homo. The irony is that we now know Homo naledi lived only about 335,000 to 236,000 years ago. At roughly the same time, the first Homo sapiens appeared in Africa. That shows that a primitive appearance does not necessarily mean a species lived in a much earlier age. But once we look at the lower body, the picture changes almost completely. The legs of Homo naledi were significantly longer than those of Australopithecus, while the feet were built much like those of modern humans. The big toe was aligned with the other toes rather than splaying outward as it does in the great apes. The arches of the feet were also well developed, helping absorb impact while walking and conserve energy over long distances. These are essential adaptations for a species that spent most of its time walking upright on the ground. This suggests that Homo naledi was exceptionally well adapted to life on the ground, even while retaining many ancient features in other parts of its body. Even so, they had not completely abandoned the world of the trees. The shoulders of Homo naledi remained relatively high. The shoulder joints faced upward, and the rib cage was conical in shape, traits commonly seen in climbing primates. Most striking of all, their finger bones were noticeably curved. This was not a random feature, but the result of long-term adaptation to regularly gripping, pulling, and climbing tree trunks or rock faces. When confronted by predators or searching for a safe refuge, climbing remained a major advantage. Perhaps the most surprising feature of all was the hand. On one hand, the curved fingers reveal an adaptation for climbing. On the other, the thumb was relatively long and robust, while the wrist shared many similarities with those of Homo sapiens and Neanderthals. These are the very features that make the precision grip possible. The ability to manipulate small objects and craft tools with remarkable control. The pelvis tells yet another story. It was relatively broad and retained many primitive characteristics, resembling Australopithecus more than later members of the genus Homo. Meanwhile, the average Homo naledi stood only about 4 feet 9 inches tall and weighed roughly 88 to 121 pounds, creating a body that was small, compact, and well-proportioned. No single body part could truly be described as either the most advanced or the most primitive. Homo naledi has fundamentally changed the way scientists think about evolution. But if the body of Homo naledi is a mosaic assembled from different stages of evolution, could its brain have worked according to the very same principle? Imagine a morning in the cradle of humankind in South Africa, about 300,000 years ago. For a Homo naledi individual standing only about 4 feet 9 inches tall and weighing an average of around 88 pounds, confronting an apex predator head-on would have been almost unthinkable. They lacked the speed of an antelope, the claws of a leopard, and the massive strength of a bear. So what allowed them to survive for tens of thousands of years in such a dangerous environment? The answer may lie in a combination of traits that have been shaped by natural selection over time. Their legs, built much like those of modern humans, allowed them to walk long distances efficiently, conserving energy as they traveled between seasonal food sources. Meanwhile, their shoulders and curved fingers, features that might seem outdated, became invaluable when they needed to climb trees or low rock faces to escape danger. The diet of Homo naledi also reflects that flexible survival strategy. They may have relied on wild fruits, seeds, tubers, insects, small animals, and even meat scavenged from carcasses whenever the opportunity arose. The fossils found at Rising Star represent every stage of life, from infants and young children to adults and the elderly. Children, with brains that were still developing, would have needed years to learn how to find food, recognize danger, and move safely through a landscape filled with predators. A mother on her own would have struggled to carry a young child, gather food, and remain constantly alert for leopards or hyenas. For this reason, many anthropologists believe that among ancient human species, caring for the young was most likely the responsibility of the entire group, rather than just the parents. Female Homo naledi were likely not limited to raising children. Standing an average of about 4 feet 9 inches tall and possessing compact bodies, they most likely took an active role in gathering tubers, fruits, seeds, insects, and other dependable food sources available throughout the year. In many modern hunter-gatherer societies, it is gathered plant foods, not meat from hunting, that provide most of the daily calories, while meat serves only as an occasional supplement. Perhaps the greatest strength of Homo naledi did not lie in muscle or brain size, but in their ability to sustain life together in the challenging landscapes of Africa. Yet nature was not their only rival. While Homo naledi was still adapting to a changing climate, an even greater transformation was unfolding across the African continent. For the first time in history, multiple human species may have shared the same land, hunted in the same landscapes, searched for the same water sources, and perhaps even seen one another. Did Homo naledi ever come face to face with our own direct ancestors? And if they did, what happened between those two human species? After millions of years of evolution, we tend to picture human history as a single line of figures standing one behind another. One species disappears, the next emerges, and eventually Homo sapiens is left standing alone. But Homo naledi has forced that familiar picture to change. When the fossils from the Rising Star Cave system were dated to roughly 335,000 to 236,000 years ago, scientists realized that at the very moment the first Homo sapiens were appearing in Africa, Earth was still home to several different human species. Each branch represented a different solution to the same challenge of survival. And Homo naledi was just one of nature's many remarkable evolutionary experiments. If we could travel back about 300,000 years, the world before us would look very different from what we imagine today. In southern Africa, Homo naledi would still be living among the familiar limestone landscapes and open grasslands. Far to the north, fossils from Jebel Irhoud in Morocco show that early Homo sapiens had already appeared by about 315,000 years ago, displaying many features of modern humans while still retaining several primitive traits. Meanwhile, in Europe and Western Asia, the ancestral populations of the Neanderthals were continuing to evolve as they adapted to an increasingly colder climate. Even farther east, in Asia, another mysterious human lineage that we now call the Denisovans was also alive, although most of what we know about them comes from ancient DNA and only a handful of fossils. Even more intriguing, many Middle Pleistocene fossils discovered in Africa still cannot be confidently assigned to any known human species, suggesting that the human evolutionary tree may contain many branches that science has yet to uncover. That means that, for a brief period in evolutionary history, Earth was home to multiple versions of humanity living at the same time. But does that mean they never encountered one another? The climate of the Middle Pleistocene changed constantly. The climate of the Middle Pleistocene changed constantly. A prolonged drought could have forced different human groups to gather around the same water source. The emergence of a new grassland might also have drawn populations that had once been separated into the same region. Imagine a morning 300,000 years ago. A small group of Homo Naledi approaches a lake in search of water and food. From the opposite shore, a group of early Homo sapiens is doing exactly the same. How would they have reacted upon seeing another human species for the first time? Would they have watched each other from a distance in curiosity? Quietly avoided one another? Or competed over the same precious resources? Archaeology still cannot answer those questions. Yet the very possibility that such encounters may have taken place makes the story of humanity far more vivid. Elsewhere in the world, we know that different human species truly did meet. Modern DNA analyses show that most people living outside Africa today still carry about 1 to 2% Neanderthal DNA, while many people in Melanesia, Papua New Guinea, and parts of Asia also carry Denisovan DNA. That proves these human species did more than simply see one another. They also had children together. But what about Homo Naledi? This remains one of the greatest mysteries of all. The hot, humid climate of southern Africa causes ancient DNA to break down rapidly, and so far scientists have been unable to recover the genome of Homo Naledi. Without DNA, we still cannot determine whether they ever exchanged genes with Homo sapiens or remained entirely separate. Another hypothesis attracting considerable attention is ecological competition. In nature, two species can influence one another simply by relying on the same food sources or occupying the same habitat. Perhaps the most extraordinary legacy of Homo Naledi is not that they eventually disappeared, but that they completely transformed the way we understand human history. Homo Naledi is more than an unusual human species discovered inside a cave in South Africa. They are a reminder that the story of evolution has always been far more complex than we once imagined. After everything Homo Naledi has revealed, the most astonishing discovery is not the sheer number of fossils or their age, but the fact that this small human species has forced the entire field of paleoanthropology to reconsider one of its most enduring beliefs. For more than a century, human evolution was often illustrated as a ladder ascending upward, with each step representing a species more advanced than the one before it. Larger brains, more sophisticated tools, and ultimately Homo sapiens standing at the top. But modern science has shown that nature has never followed such a straight path. And Homo Naledi stands as one of the strongest pieces of evidence for that reality. What puzzles scientists is not that Homo Naledi was either too modern or too primitive, but that it was both at once. They possessed brains measuring only about 28 to 37 cubic inches, dramatically smaller than the average Homo sapiens brain of roughly 82 cubic inches. Yet their bodies displayed many of the traits of highly efficient long-distance walkers. Their hands were dexterous enough to perform precise movements, and they lived between approximately 335,000 and 236,000 years ago, precisely when the first Homo sapiens had already appeared in Africa. That combination alone is enough to overturn the idea that modern traits must always emerge together in one fixed sequence. The concept that paleoanthropologists now use to explain this phenomenon is known as mosaic evolution. Different parts of the body can evolve at different rates if doing so provides a survival advantage. Homo Naledi has also changed the way we evaluate intelligence and adaptability. For many years, brain size was often regarded as the single most important measure. Yet, as we have seen, size is only one part of the story. What matters even more is how biological traits work together to create a complete survival strategy. Another profound change brought about by Homo Naledi is the way scientists think about the gaps in the fossil record. Before 2013, almost no one knew this human species had ever existed. Is Homo Naledi truly a unique exception, or simply the first of many human species we have yet to discover? The history of science has repeatedly shown that every major discovery tends not to end a debate, but to open dozens of new questions. We still have no DNA from this species because Africa's hot and humid climate makes genetic material extremely difficult to preserve. The hypotheses that they regularly used fire, created cave engravings, or engaged in symbolic behavior are still being tested and have not yet reached broad scientific consensus. Perhaps the greatest lesson Homo Naledi leaves behind is not whether they were our ancestors, but how they changed the very questions we ask about our origins. The history of the genus Homo is more like a sprawling bush with countless branches diverging, evolving side by side, and many of them quietly disappearing. Homo sapiens was not a predetermined destination from the beginning, but simply the branch that survived through countless changes in climate, environment, and evolution. And that may be the greatest legacy of Homo Naledi. They did not change history by building civilizations or leaving behind cities of stone. They changed history by forcing modern humans to abandon an overly simple story about their own origins. Yet even after all these discoveries, one final mystery remains. What truly happened to Homo Naledi? Why did a human species that survived for hundreds of thousands of years disappear while leaving behind so few traces? And was that disappearance truly the end, or merely a missing chapter in the evolutionary story that we are still writing? For more than 300,000 years, dozens of Homo Naledi individuals lay silently in the darkness. leaving behind no cities, no written language, and no monuments. Perhaps the most astonishing fact is not that Homo naledi once existed, but that a single cave system in South Africa was enough to force scientists to rewrite entire chapters of the story of human origins. And if Rising Star was able to guard that secret for hundreds of thousands of years, then it is entirely possible that beneath other layers of rock across Africa, there are still unknown human species waiting to be discovered, waiting for the next breakthrough that could once again transform everything we think we know about the history of our own kind. Before there were kings, before there were pyramids, even before humans knew how to write their own names, there was once a human species that built its own empire for nearly 2 million years. No borders, no cities, no civilization. When ice ages descended, when the climate was thrown into chaos and countless species disappeared, they endured. Homo erectus. What allowed this primitive human species to survive longer than any other member of the genus Homo? That very secret changed the course of human evolution. If you could travel back about 2 million years and stand in the East African Rift Valley, you would see no cities, no agriculture, and no trace of civilization. Before you would stretch vast grasslands broken by open woodlands, where ancient elephants, giant hippos, hyenas, and saber-toothed cats ruled the landscape. In the midst of that dangerous world, a new human species emerged, Homo erectus. They were neither the strongest nor the most intelligent species of their time. Yet they accomplished something no human species had ever achieved before. They became the first members of the genus Homo to successfully leave Africa, beginning a journey that would eventually carry them across nearly the entire Old World. What makes this migration even more remarkable is that it happened long before humans had maps, wheels, boats, or draft animals. Each group simply moved a few more miles in search of water, followed migrating herds, or abandoned lands where food had become scarce. But when those small steps were repeated over thousands of generations, they became one of the longest migrations in the history of evolution. From East Africa, traces of Homo erectus gradually appeared throughout the Levant, the Caucasus, East Asia, and eventually Southeast Asia, spanning more than 6,200 miles. One of the most important pieces of evidence comes from Dmanisi in Georgia. Fossils dating to about 1.8 million years ago reveal that the earliest members of the genus Homo left Africa much earlier than scientists had once believed. That journey continued. At Zhoukoudian, near Beijing, the fossils of Peking man demonstrate that Homo erectus adapted to temperate climates with cold winters and food supplies that changed with the seasons. Farther south, on the Indonesian island of Java, Java Man shows that they had already arrived by about 1.5 million years ago, and the last surviving populations may have persisted until roughly 117,000 to 108,000 years ago. That means when Homo sapiens first appeared in Africa around 300,000 years ago, the final communities of Homo erectus were still living in Southeast Asia. But the success of Homo erectus was measured by more than the distance they traveled. It was defined by the environments they conquered. They survived the hot, dry grasslands of East Africa, endured the cold winters of the Caucasus, adapted to the temperate climates of northern China, and thrived in the humid tropical forests of Java. While most animals flourish in only a limited range of environments, Homo erectus was able to survive across many different ecosystems without relying on complex technology to reshape nature. They did not force nature to adapt to them. Instead, they changed themselves to adapt to nature. Imagine a Homo erectus individual stepping into a land unlike anything they had ever known. Everything was unfamiliar. Different predators, different plants, different water sources, and a different climate. In your opinion, what would determine survival? Strength, intelligence, or the ability to learn and adapt? The answer may not lie within Homo erectus itself, but within Earth. About 2 million years ago, East Africa was not a stable land. The climate was constantly changing because of variations in Earth's orbit, tectonic activity within the East African Rift System, and climatic fluctuations during the early Pleistocene. Lakes formed and then disappeared, dense forests shrank into grasslands, and later gave way to shrublands and open woodlands. For many animal species, this was a disaster, but for our ancestors, that very instability became evolution's harsh training ground. An organism adapted to only one environment is more likely to fail when that environment changes. In contrast, an organism capable of changing how it finds food, moves, and survives has a greater chance of remaining alive. Imagine two groups of early humans living in East Africa, with one group knowing only how to find food in the forest. The other group, in addition to gathering fruit, also knows how to dig for tubers, hunt small animals, and make use of animal carcasses. When drought causes the forest to disappear, the first group quickly falls into crisis. Homo erectus was almost never able to live long enough in a stable environment. They were forced to adapt again and again. Every climatic change was like a test, and over nearly 1.9 million years, they passed countless tests like it. The difference becomes even clearer when compared with Homo habilis. Homo habilis was one of the earliest species of the genus Homo known to make stone tools, but it still lived mainly in heavily wooded environments, and its range was largely limited to Africa. Meanwhile, Homo erectus had a more varied diet, traveled farther, and was prepared to exploit many different ecosystems. They did not depend on a single food source, environment, or survival strategy. That diversity itself helped them reduce the risks created by nature's unpredictable changes. Scientists also believe that unstable environments may have contributed to the development of cognition. When lakes dried up, animal herds changed their migration routes, or the rainy season arrived late. Homo erectus had to remember the landscape, observe natural patterns, and coordinate with members of the group to make decisions. What made Homo erectus exceptional was not that they were born superior to other species of the genus Homo. Earth itself continuously challenged them through drought, climate change, and shifting ecosystems. Homo erectus was not created in spite of a harsh planet, but was forged by that very planet. But to transform adaptability into migration stretching more than 6,200 miles, Homo erectus still needed another crucial advantage: a body designed to travel farther, endure longer, and move more efficiently than any ancestor before them. The clearest evidence comes from the Turkana boy skeleton, KNM-WT 15,000, discovered near Lake Turkana in Kenya and dated to about 1.5 million years ago. When he died, the boy was only about 8 to 11 years old, yet he already stood nearly 5 feet 3 inches tall. If he had reached adulthood, scientists estimate that he might have grown to nearly 6 feet. More important than his height were his body proportions: long legs, shorter arms, a narrow pelvis, and a more compact rib cage. This was no longer a body suited for climbing trees, but one optimized for walking and traveling across vast landscapes. At first glance, longer legs may seem like only a small change, but in evolution, they offered an enormous advantage. A longer stride meant fewer steps were needed to cover the same distance, conserving energy across thousands of steps each day. Homo erectus did not necessarily run faster than other species, but they could travel farther using the same amount of energy. In a world where food and water sources were constantly changing location, endurance mattered more than speed. That was also one of the key differences between humans and many predators. A cheetah can reach nearly 70 miles per hour, while a horse can run at about 44 miles per hour. But Homo erectus does not appear to have evolved to become the fastest running creature. Arched feet helped absorb impact. The big toe was aligned with the other toes to produce stronger propulsion, and the Achilles tendon functioned like a natural spring, storing and then releasing energy with every step. Together, these traits transformed Homo erectus into one of the most efficient long-distance walking machines evolution had ever created. But traveling far was still not enough. East Africa nearly 2 million years ago was often extremely hot, with midday temperatures that could exceed 100 degrees Fahrenheit. Many animals were forced to rest to avoid overheating. Meanwhile, our ancestors may have possessed another advantage: the ability to cool the body efficiently. Modern humans have approximately 2 to 4 million eccrine sweat glands, more than most primates. This would have allowed them to keep moving in the heat, while many predators had already been forced to stop. Based on these characteristics, researchers Dennis Bramble and Daniel Lieberman proposed the persistence hunting hypothesis. According to this hypothesis, Homo erectus did not need to be faster than their prey. They only needed to keep following it for many hours. Antelope or zebras could accelerate very quickly, but they would also overheat and become exhausted rapidly. Meanwhile, humans would continue moving forward. In the end, the prey might collapse not because it had been caught, but because it no longer had the strength to keep running. Today, some hunter-gatherer groups, such as the Sand People of southern Africa, have still been documented using similar hunts, showing that this strategy has a clear biological foundation, although how common it was during the time of Homo erectus remains under study. What is fascinating is that Homo erectus did not possess the largest brain within the genus Homo. So why did they still become the longest surviving human species? We often assume that a larger brain means greater intelligence, but evolution does not work that way. The brain is the most energy-demanding organ in the body. In modern humans, it accounts for only about 2% of body weight, but consumes roughly 20% of the body's resting energy. In a prehistoric environment, where every meal required hours of searching or hunting, an overly large brain could also become a burden. What natural selection favored was not the largest brain, but the brain that delivered more benefits than the costs required to sustain it. This is clearly reflected in the evolution of the genus Homo. Homo habilis had a brain volume of approximately 510 to 700 cubic centimeters. In Homo erectus, that figure increased to around 600 to 1,100 cubic centimeters, and in some later populations reached nearly 1,250 cubic centimeters, still smaller than the modern Homo sapiens average of 1,300 to 1,400 cubic centimeters. Yet with that brain, Homo erectus became the first human species to leave Africa, adapt to a wide range of environments, and survive for nearly 1.9 million years, longer than any other known human species. This shows that brain size was not the only deciding factor. Archaeological evidence suggests that Homo erectus possessed a basic ability to plan. They could remember the locations of water sources, track the migration routes of animal herds, and move before the environment became scarce. Imagine a group of Homo erectus living near Lake Turkana. When the dry season arrived and the antelope herds began to leave, they did not wait until the food was gone before taking action. They left early because they had learned the patterns of nature through years of observation. That was already a major advance in the ability to anticipate the future. That brain also helped them construct a map in memory. During journeys stretching across dozens or hundreds of miles, they had to remember where seasonal water could be found, where high-quality stone was available for making tools, and which areas with many predators needed to be avoided. This formed the foundation for their ability to expand their range across Africa and then into Eurasia. More importantly, the brain of Homo erectus was developed enough for them to learn from one another. Acheulean hand axes with nearly identical designs have been found from Africa to Western Asia and remained in use for more than 1.5 million years. Knowledge began to pass from one generation to the next, instead of disappearing with each individual. Perhaps Homo erectus had reached what engineers today would call optimization. Homo erectus did not possess the largest brain, but they possessed the brain best suited to their world. Looking back, the success of Homo erectus did not come from any single trait. Their bodies allowed them to travel far, while their brains helped them know where to go, when to change, and how to survive. Perhaps evolution was never moving toward creating the most intelligent organism, but toward creating the organism capable of adapting most efficiently. But the ability to think alone was still not enough to sustain a species for nearly 2 million years. What truly transformed that intelligence into power was a technology so simple that it remained almost unchanged for more than 1.5 million years. Why could a single design endure longer than the entire history of Homo sapiens? Around 1.76 million years ago, at Kokisole near Lake Turkana in Kenya, the first Acheulean hand axes appeared. From East Africa, this technology followed Homo erectus across Western Asia, South Asia, and many regions of Europe. What astonishes archaeologists is not only its vast geographic spread, but also the remarkable consistency of its design. Although they were made hundreds of thousands of years apart and separated by thousands of miles, many of these hand axes still share nearly identical teardrop or leaf-like shapes. This suggests that their makers were not simply striking stone at random. They envisioned the final product in advance, selected the right kind of stone, and calculated each blow to create the desired form. Compared with the simpler Oldowan tools that came before, Acheulean technology represented a major advance in thinking. More importantly, it was a highly versatile design. With a single hand axe, Homo erectus could cut meat, skin animals, chop branches, dig for roots, break bones to extract marrow, and work wood. For Homo erectus, the Acheulean hand axe was the multi-tool of prehistory. Even more significant is the fact that the skill required to make these tools was not an inborn instinct. To create a balanced hand axe, the maker had to know how to select suitable stone, understand the fracture patterns of the stone core, and control the force of every strike. A single mistake could ruin the entire piece of stone. This suggests that younger individuals had to observe adults, practice for long periods, and only then become skilled. One question is often asked: why did Homo erectus make almost no fundamental changes to this technology for more than 1.5 million years? In nature, a technology does not need to change if it continues to solve the problem of survival effectively. The modern hammer has retained its basic design for thousands of years, not because humans lack creativity, but because it is already highly effective. The Acheulean hand axe was much the same. It was sharp enough, durable enough, easy to make, and suitable for many different environments. Evolution does not reward novelty. It rewards what truly works. Of course, Acheulean technology was not completely unchanging. Archaeologists have recorded regional differences in size, thinness, and napping techniques due to variations in raw materials and local environments. But the core principle of the tool remained intact for more than 1 million years. That stability reflects a survival strategy tested by nature through countless shifts in climate and environment. Looking back, the Acheulean hand axe was more than a tool made of stone. It was evidence that Homo erectus could plan, learn, and pass on knowledge, laying the foundation for the technological culture of the entire genus Homo. But no matter how versatile it was, it could not provide warmth during a cold night, drive away predators, or transform raw food into a source of nutrition that was easier to absorb. To truly change their fate, Homo erectus still had to master a force greater than any stone tool: fire. And that flame may have opened the most important turning point in the evolutionary history of humankind. However, the great question is not when humans first saw fire. Wildfires caused by lightning had existed long before humans appeared. But when they learned to preserve it and use it deliberately. Although the exact timing is still being studied, a growing body of archaeological evidence suggests that Homo erectus had controlled fire by around 1 million years ago, and possibly even earlier in some regions. One of the strongest pieces of evidence comes from Wonderwork Cave in South Africa. There, scientists discovered plant ash, burned bones, and traces of combustion nearly 100 feet inside the cave. What matters is that these materials burned in place rather than being carried in from outside by the wind. Dating to around 1 million years ago, this is considered reliable evidence that a population of Homo, most likely Homo erectus, knew how to maintain fire within its living space. Another site is Gesher Benot Yaakov in Israel, dating to around 790,000 years ago. There, archaeologists discovered multiple clusters of burned stones, seeds, wood, and fish bones concentrated in separate areas, resembling hearths that had been used repeatedly. This suggests that humans not only preserved fire, but also organized their living space around it. The ability to preserve fire alone was enough to transform life completely, as cooked food became softer, easier to chew, and easier to digest, while also greatly reducing bacteria and parasites. Anthropologist Richard Wrangham has argued that cooking may have allowed the body to absorb more energy, creating conditions that supported brain development, although the exact timing of this process is still being studied. Despite continuing debate, most scientists agree that cooking was a major turning point in the evolution of the genus Homo. Fire also changed the rhythm of human life, as before that, when the sun went down, darkness meant danger. But firelight extended waking hours, creating time and space to repair tools, share food, care for children, and pass on experience. Many researchers believe that these hours spent gathered around the fire may have encouraged social cooperation and laid the foundation for the development of communication, although we cannot prove this with certainty. Just as importantly, fire helped Homo erectus expand its range. as when they moved into the temperate regions of Eurasia, where winter temperatures could fall to 32 degrees Fahrenheit or lower. Fire provided warmth, drove away many predators, and helped them adapt to environments that had previously been extremely difficult to survive in. For the first time, human limits were no longer determined entirely by climate, but increasingly by the ability to use technology. Looking back at the journey of Homo erectus, we can see that their success did not come from a single invention. Their bodies allowed them to travel far, their brains allowed them to plan, and their tools allowed them to exploit resources. Fire allowed them to harness energy and expand the limits of survival. It was the combination of all these factors that created a human species capable of surviving for nearly 2 million years. But one greater question remains. If Homo erectus possessed so many advantages, why did they ultimately disappear while Homo sapiens became the only surviving human species? The true secret did not lie in any single trait, but in the ability to combine them all into one unified strategy. The ability to adapt to an ever-changing Earth. Throughout most of the Pleistocene, Earth's climate repeatedly shifted between glacial and interglacial periods. Temperature, rainfall, sea level, and vegetation changed many times. Forests could turn into grasslands, only to be replaced later by shrublands or semi-deserts. For many animal species, a single major environmental shift was enough to cause populations to decline or disappear entirely. Yet the fossil record shows that Homo erectus continued to survive across Africa, Western Asia, East Asia, and Southeast Asia. This suggests that they did not depend on a single ecosystem, but could adapt to many different environments. Research from the Smithsonian's Climate and Human Evolution program also indicates that periods of intense climate instability created strong selective pressure favoring adaptability in human ancestors. Evolution does not necessarily favor the strongest or the most intelligent individuals, but those capable of changing when circumstances change. That ability is also reflected in their diet, as analyses of carbon isotopes in tooth enamel and patterns of dental wear suggest that Homo erectus did not follow a fixed menu. Depending on the region, they may have hunted large animals on open grasslands, dug for roots, gathered fruit, scavenged carcasses, or exploited many other food sources. Imagine two groups of early humans facing the same drought, with one group knowing only how to hunt a single animal species around a lake. When the lake dries up and the animals disappear, the group falls into crisis. The other group immediately changes its strategy, digging for roots, gathering fruit, hunting smaller animals, or following migrating herds. The second group clearly has a greater chance of survival. Homo erectus appears to have repeatedly chosen that strategy. They did not cling to one fixed way of life, but continually adjusted to the environment. This ability to adjust quickly within only a few generations helped them expand from the grasslands of East Africa to the temperate regions of Eurasia and the tropical forests of Indonesia. This may be the greatest lesson left by Homo erectus. Evolution is not a race to create the strongest or most intelligent organism, but a process that selects those able to adapt most effectively. In a world that is always changing, flexibility is often more valuable than strength. But what allowed knowledge to pass from one generation to the next, transforming the experience of individuals into the strength of an entire species? One of the most fascinating pieces of evidence comes from Dmanisi in Georgia, where fossils dating back around 1.8 million years have been preserved. There, scientists discovered an individual who had lost nearly all of their teeth but continued to live for a considerable period of time. In an environment where food mainly consisted of meat, roots, and hard seeds, this would have been extremely difficult if the individual had been forced to survive alone. Although we cannot say with certainty that this was altruism in the modern human sense, many researchers believe the most reasonable explanation is that the individual received help from other group members in the form of soft food, or food that had been cut into smaller pieces. This suggests that Homo erectus did not merely live alongside one another, but also cared for weaker members of the group. Older individuals were not only those who had survived longer, but also living stores of experience. They knew where seasonal water sources could be found, which direction animal herds usually migrated, and how to endure droughts that had occurred before. When that experience was shared with younger generations, the entire group gained a greater chance of survival. The clearest evidence of knowledge transmission is the Acheulean tradition. For more than 1.5 million years, bifacial hand axes preserved the same basic design principles from Africa to Western Asia, South Asia, and many parts of Europe. When groups of Homo erectus migrated into new lands, they did not begin from nothing. They carried with them techniques for making tools, hunting experience, methods for maintaining fire, and ways of coordinating within the group. This allowed them to adapt far more quickly than if every individual had been forced to learn everything alone, and knowledge became a shared resource belonging to the entire community. It was this accumulation of knowledge that helped them become the longest surviving species of Homo in history. Yet the greatest paradox still lay ahead. In the end, they disappeared from Earth. What caused this champion of survival, which endured for nearly 2 million years, to give way to Homo sapiens? According to dating studies published in Nature in 2019, the last populations at Gendong on the island of Java survived until around 117,000 to 108,000 years ago. This also means that Homo erectus and Homo sapiens coexisted on Earth for nearly 200,000 years, although in different regions. Therefore, the idea that Homo erectus disappeared as soon as modern humans emerged does not fit the archaeological evidence. So what happened? Science has not identified a single cause. Most researchers believe that the extinction of Homo erectus resulted from several factors acting together over a long period of time. One of the most important factors was environmental change. During the final phase in Java, the climate became wetter, and grasslands and open woodlands were gradually replaced by tropical rainforests. The skills that had once helped Homo erectus succeed in open landscapes no longer offered the same advantages. Environmental change also caused populations to become fragmented. As human groups were isolated by dense forests, rivers, or shifting sea levels, their numbers gradually declined, along with their genetic diversity. Modern conservation biology shows that small populations are highly vulnerable to disappearing, even without a major catastrophe. Perhaps the last groups of Homo erectus were drawn into the same downward spiral. Another hypothesis involves the emergence of more advanced Homo species. In fact, many scientists believe that by the time Homo sapiens reached Southeast Asia, most populations of Homo erectus may already have disappeared. Even so, the direction of evolution was changing. Later species such as Homo heidelbergensis, Neanderthals, and especially Homo sapiens continually improved their technology, expanded their behavioral flexibility, and adapted more rapidly to new environments. This is also the paradox at the heart of the Homo erectus story. For more than 1.5 million years, Acheulean technology changed very little because it worked so effectively. The disappearance of Homo erectus was therefore remarkably quiet. The fossil record does not preserve a single doomsday, but instead shows populations becoming increasingly rare before disappearing one by one at different times. This is also how most species on Earth come to an end. Not in a single moment, but through thousands of small changes accumulating over time. But perhaps the most important thing to remember is not their disappearance, but the legacy they left behind. Homo erectus proved that evolutionary success does not belong to the strongest or the most intelligent species, but to the one capable of adapting to a changing world. They sustained that success for nearly 1.9 million years, an achievement that Homo sapiens is still far from matching. Perhaps the greatest lesson left behind by Homo erectus lies not in how they lived, but in the reminder that in evolution, no species is guaranteed to survive forever. Every civilization has a beginning. But the deeper archaeologists dig, the more they realize something surprising. The roots of civilization may have begun far earlier than humanity once believed. So what suddenly made the wheel of time spin faster? The story begins in a world just waking up after the Ice Age. If Göbekli Tepe makes us question whether the story of civilization began earlier than anyone once believed, then to find the true starting point, we must travel back several thousand years further. Before agriculture, before cities, and before states, there was a small decision that changed the course of human history forever. For the first time, people chose to stay. For nearly 300,000 years, Homo sapiens lived as nomads. They moved with migrating herds, followed the changing seasons, and searched for reliable sources of water. When food became scarce, entire communities moved on. There were no permanent villages, no territorial boundaries, and not yet any concept of a homeland. In the Levant, between roughly 15,000 and 11,500 years ago, the Natufian communities chose a different path. They continued hunting, gathering, and harvesting wild wheat and barley, yet they also began building permanent settlements. Archaeological research and radiocarbon dating show that in many places, sedentary life appeared before agriculture became the primary source of survival. At the site of Ain Malaha, archaeologists uncovered stone houses that were repaired and occupied across multiple generations. Inside were basalt grinding stones weighing dozens of kilograms, along with sickle blades coated in a glossy layer of silica, the unmistakable traces of long-term grain harvesting. This suggests that the Natufians were not yet farmers, but they had already developed systematic ways of exploiting wild grain fields and had begun storing food to survive periods of scarcity. An even greater transformation emerged in the way they treated their dead. The Natufians began burying their ancestors beneath house floors or beside their settlements. At Hilazon Taktit, a woman of ritual status was interred alongside turtle shells, eagle wings, and numerous rare objects. From that point on, a dwelling was no longer merely a shelter. It became a place where memory, belief, and collective identity were preserved. When ancestors rested beneath the very ground on which people lived, that land acquired a new meaning for the first time. It became a homeland. Ancient DNA studies also reveal that multiple generations of Natufians lived continuously within the same settlements while still marrying into neighboring groups. This demonstrates that they were simultaneously creating stable communities and maintaining networks of exchange with the wider world. At Ain Malaha, archaeologists discovered the approximately 12,000-year-old grave of a woman buried alongside a young dog. It is one of the earliest direct archaeological pieces of evidence for the relationship between humans and dogs. From hunting companion to member of the community, dogs gradually became part of human society, marking the beginning of the longest biological alliance in human history. Humans did not settle down because they had already learned how to farm. Rather, settlement itself created the pressure that forced them to invent agriculture in order to support growing populations on the same land. Villages were not the result of the agricultural revolution. They were the foundation that made it possible. Yet just as these first communities were beginning to put down roots, Earth suddenly changed the rules of the game. A cold period, lasting more than a millennium, was approaching, reducing natural food supplies and pushing these young settlements into the greatest survival crisis they had ever faced. It was this climatic upheaval that would compel humanity to take the boldest step in its history, the invention of agriculture. About 12,900 years ago, as the global climate was gradually warming after the last ice age, the northern hemisphere suddenly fell into an intense cold period known as the Younger Dryas. This phase lasted about 1,200 years, from 12,900 to 11,700 years ago, and is considered one of the clearest abrupt climate shifts ever recorded in Earth's recent history. In the Levant, where the Natufians had begun to settle down, the climate became colder and drier. Fossil pollen analysis shows that forests became thinner, grasslands expanded, and wild wheat and barley populations declined significantly. Gazelle herds also changed their migration routes in search of new food sources. Suddenly, settlement itself became a disadvantage. Nomads could leave when food ran out. But communities that had built stone houses, dug food storage pits, and buried their ancestors beneath their floors could not easily abandon everything. Archaeology shows that many Natufian villages shrank or were abandoned, while some communities were forced to return to a seasonal mobile lifestyle. Yet not everyone left. Some people chose to stay, and that decision changed history. They began actively shaping their living environment, gathering the best seeds, planting them near their homes, then returning to care for them and harvest them in the following season. This was not yet full agriculture, but it was the first time humans tried to make nature produce more food instead of merely taking what was already available. One of the clearest pieces of evidence comes from the site of Tel Abu Huraira along the Euphrates River. The people living there exploited cereals with increasing intensity and began unintentionally selecting plants with traits that made harvesting easier. Across many generations, thousands of small repeated decisions quietly changed the genomes of cultivated plants. This was the beginning of domestication. Scientists today do not consider the Younger Dryas to be the only cause of agriculture. The research consensus suggests that agriculture emerged from many factors working together: climate change, population pressure, the development of settled communities, and the accumulation of knowledge over thousands of years. Looking back, this is an astonishing paradox. Earth seemed to be trying to pull humanity back into the age of hunting and gathering. Yet that very crisis pushed humans toward an entirely new evolutionary path. It was not war, not a king, and not a single genius, but climate itself that forced humanity, for the first time, to learn how to change nature instead of only adapting to it. That was the turning point that opened the age of agriculture, but it was also the beginning of another paradox. Life for the first farmers would not be easier than life for hunter-gatherers. They worked harder, faced more disease, and depended on harvests more than ever before. So why did humanity still choose that path? They were no longer only searching for food. They had learned how to create it. And from here, humanity stepped into the decision that would transform all of history, the agricultural revolution. At first glance, this seemed like an obvious step forward. Farming and animal herding promised a more stable life than hunting and gathering. But archaeology tells a different story. For hundreds of thousands of years, hunter-gatherer groups used hundreds of different plant and animal species, creating a diverse diet. By contrast, the first farmers in the Fertile Crescent became increasingly dependent on only a few crops such as wheat and barley. Just one failed harvest could push an entire community into famine. In return, agriculture offered an advantage that hunting and gathering could never provide. It produced more food on the same area of land. That was the turning point. When food supplies became more stable, more children survived, populations grew faster, and settlements expanded. Jericho became one of the largest pre-pottery Neolithic settlements from around 9,500 BCE. Murghar preserves early evidence of farming and herding in South Asia from around 7,000 BCE. And Çatalhöyük was home to thousands of people living together in a dense community, reflecting a social scale that earlier hunter-gatherer groups had never reached. But that victory came at a cost. Studies of human skeletons from the early agricultural period showed that average height declined, tooth decay increased, and bones and joints carried many signs of heavy labor. The lives of the first farmers were not healthier. In many places, they were even harder than those of their hunter-gatherer ancestors. Another change was also unfolding quietly. As humans lived in concentrated settlements and kept livestock close to their homes, the distance between people and animals narrowed. This created the conditions for many animal pathogens to gradually adapt and spread to humans. Modern studies show that this process laid the foundation for many infectious diseases that would later emerge in densely populated societies. That is the greatest paradox of the agricultural revolution. If we judge it by the life of each individual, it was not necessarily a better choice. But if we judge it by the ability to feed more people, expand populations, and build increasingly larger communities, agriculture won almost completely. Most importantly, for the first time, humans possessed things they could not carry with them when they left: fields, food stores, and livestock. And it was precisely when wealth began to accumulate that an entirely new question appeared: who owned it? The agricultural gamble finally delivered its greatest reward: surplus. And from that surplus, humans unknowingly invented a concept that would shape all of history that followed: wealth. For hundreds of thousands of years of hunting and gathering, possessions were almost limited to what a person could carry: a spear, a stone knife, or a few personal objects. No one could accumulate too much, because tomorrow the entire group might move on again. But with settlement and farming, everything changed. Fields, food stores, livestock, and houses could last for many years, even many generations. A family with a good harvest could keep more seeds, expand its fields, raise more livestock, and continue increasing its wealth. After only a few generations, the gap between rich and poor began to appear. Archaeology shows that in early Neolithic communities such as Çatalhöyük, differences were still small. But in later societies in Mesopotamia, larger houses, larger food stores, and graves containing many valuable objects reflected the accumulation of wealth by certain families. Inequality did not appear immediately, but it had begun to form. When wealth could be passed from parents to children, the family also became the first economic unit in history. Inheritance rights, ownership rights, and the idea of our land gradually replaced the relatively equal sharing lifestyle of hunter-gatherer groups. That accumulation quickly drove trade. The volcanoes of Anatolia provided obsidian for making sharp blades, while Mesopotamia had fertile alluvial soil, and other regions possessed copper, salt, or natural bitumen. Instead of producing everything themselves, communities began exchanging with one another. Modern geochemical analyses show that many obsidian artifacts in the Levant originated in Anatolia, more than 800 kilometers away. These discoveries prove that long before wheels or roads existed, humans had already built long-distance trade networks connecting many regions of Western Asia. Trade also created labor specialization. Not everyone farmed. Some people specialized in pottery, metallurgy, weaving, or transporting goods. Society became more efficient, but also more complex. As goods, property, and transactions multiplied, human memory began to become the greatest limit. How could anyone remember how much grain remained in each storehouse? Who had exchanged grain for livestock? Which family still owed a debt from the previous harvest? A small village could rely on memory, but a society of thousands of people could not. And to solve that very problem, humanity would create an invention that changed history even more profoundly than the wheel: writing. What is fascinating is that humanity's first information revolution did not begin with books, poems, or stories about the gods. It began with bookkeeping. Around 8000 BCE, in Mesopotamia, archaeologists found thousands of clay tokens. Small pieces of clay in different shapes, such as cones, spheres, and discs. According to the research of archaeologist Denise Schmont-Besserat, each shape represented a type of goods or a unit of counting, such as barley, oil, sheep, or goats. They can be seen as the first transaction records in history. Imagine a farmer bringing 20 sacks of grain to a temple storehouse. Instead of relying only on spoken memory, the manager would give him the corresponding number of tokens. That way, both sides knew exactly how many goods had been delivered without depending on memory. But as exchange became more frequent, a new problem appeared. What if someone lost or switched the tokens? To solve that, the Sumerians placed the tokens inside a hollow clay ball called a bulla. then sealed it with the cylinder seal of the owner or administrative authority. If the seal was broken, everyone would immediately know that someone had interfered with what was inside. A bulla can be understood like a sealed envelope, and the seal like a signature today. Then one very simple idea changed history. Instead of shaping tokens and placing them inside a bulla, why not press their symbols directly onto the surface of the clay? Around 3,400 to 3,200 BCE, in the city of Uruk, they developed into cuneiform, the earliest complete writing system we know of. What is surprising is that the first texts did not tell stories of kings or heroes. Most were simply accounting records. How much grain had entered the storehouse? Who received rations? How many livestock there were, or who still owed taxes? On one clay tablet appears the name Kushim, which many scholars consider one of the oldest personal names ever recorded. That reveals a very interesting truth. Writing was not born to tell stories. It was born to manage a society that was becoming increasingly complex. Along with writing, an entirely new profession also appeared, the scribe. They spent many years learning hundreds of signs, practicing writing on clay tablets with reed styluses, and recording every activity of temples and governments. They tracked grain stores, taxes, contracts, and transactions. If farmers created the food that fed society, then scribes created the information order that allowed society to function. Writing did the same thing more than 5,000 years ago. For the first time, information no longer depended on the memory of a single human being. It could continue to exist long after the writer had died. Thanks to that, laws could be preserved, ownership could be confirmed, contracts could be protected, and food stores could be managed accurately. A small village could still function through memory, but a city with tens of thousands of residents could not. It was precisely when humans learned to store information outside the brain that they also gained the conditions needed to build the first cities. And from those cities, civilization would enter an entirely new chapter. Between roughly 4,000 and 3,100 BCE, along the basin of the Tigris and Euphrates rivers, the city of Uruk grew at a speed never seen before. At its height, Uruk covered about 250 to 400 hectares and had an estimated population of 40,000 to 50,000 people. For nearly 300,000 years before that, humans had mostly lived in groups of a few dozen individuals. Now, for the first time, a massive community had appeared. Seen from above, Uruk looked more like a living body than a collection of houses. Each resident was like a cell, and what kept that body functioning was not the strength of any single person, but an entire system. This is the key difference between a village and a city. A village depends on people who know one another. A city depends on rules, information, and the division of labor. At the center of Uruk stood the Inanna temple complex, dedicated to the goddess Inanna. It was also the economic and administrative center of the city. Food from the fields was brought into the temple storehouses, recorded in cuneiform, and then distributed to potters, metalworkers, builders, and scribes. Because of this, for the first time, people could spend their entire lives doing only one job. It was this specialization that allowed labor productivity and technology to develop faster than ever before. To feed that body, Uruk built a network of canals connecting the Euphrates River with fields and residential areas. At first, they were used for irrigation, but they quickly became vital transportation routes. Boats carrying grain, wool, oil, and raw materials moved back and forth every day. If Inanna was the heart, then the canals were the blood vessels, carrying life to every corner of the city. And writing was the nervous system. Without clay tablets recording information, no one would know how much grain remained in storage, who had received rations, or which merchant caravan had just arrived. One clear example is the tens of thousands of beveled rim bowls discovered at Uruk. Many archaeologists believe they were produced in nearly standardized sizes to distribute grain rations to a large labor force. Uruk was also the center of a vast trade network. Archaeology has found copper from Anatolia and Iran, obsidian, wood, and many valuable raw materials transported there from hundreds, even thousands of kilometers away. During the same period, sailboats became increasingly common on river routes. While the wheel, appearing around 3,500 BCE, was first used to transport goods before serving warfare, when combined with irrigation, trade, and writing, these inventions turned Uruk into a system that could operate on its own and keep expanding. But as more cities like Uruk developed, a new question quickly appeared. Who would manage all of these living bodies? The answer would open the next chapter of human history, the birth of the state. When the first cities were already functioning like living bodies, a new question immediately appeared. One city could manage itself, but when many cities shared the same river, competed for fertile land and trade routes, who would set the rules of the game? That question led humanity into an entirely new era, the birth of the state. Between roughly 3,100 and 2,300 BCE, the lower Mesopotamian region formed a series of Sumerian city-states such as Uruk, Ur, Lagash, Kish, Eridu, and Nippur. Each city-state had its own territory, central temple, irrigation system, army, and administrative apparatus. For the first time in history, humans did not belong only to a family or tribe. They became citizens of an institution. Clay tablets excavated in Mesopotamia recorded the collection of taxes in barley, the division of land, the distribution of rations to workers, the counting of livestock, and the signing of contracts. For the first time, power was enforced through writing, records, and administration, not only through military strength, but as wealth increased, conflict also became unavoidable. Land, water sources, and trade routes became strategic assets. War was no longer merely conflict between small tribes, but became organized warfare. The steel of the vultures from the city-state of Lagash shows troops equipped in a coordinated way, fighting in formation under unified command. This is one of the earliest pieces of evidence for an army organized and sustained by the state. Amid the constant competition between city-states, around 2334 BCE, one figure completely changed the history of the Near East: Sargon of Akkad. After conquering many Sumerian city-states, he built the Akkadian Empire, often considered the first multi-territorial empire recorded in history. Sargon's greatest achievement was not only victory on the battlefield, but the ability to manage a vast territory. He appointed loyal governors, maintained a network of scribes, issued written orders, and controlled tribute collection across the entire empire. For the first time, a person could obey the command of a king they had never met in their entire life. From here, many concepts familiar to us today began to take clearer shape. Borders to define territory, officials to represent the government, taxes to maintain the state apparatus, and army, diplomacy to maintain relations between states, and laws to resolve disputes. Before it, the Sumerians had the Code of Ur-Nammu, around 2100 to 2050 BCE, one of the oldest known written law codes. What is astonishing is that after more than 5,000 years, the modern WUFO operating on foundations laid in the time of Sumer, taxes, law, administration, records, borders, and the power of institutions. But as power and wealth became increasingly concentrated, a new chapter also began to open, the chapter of empires, inequality, and wars that would shape the rest of human history. From a single seed planted in ancient alluvial soil, humans created a constantly evolving system for managing society. Although the first kingdoms have fallen into ruins, their legacy does not lie in collapsed stones, but in the very way we think and operate the world today. The dawn of civilization has never truly ended. It is only transforming into harsher and greater chapters in the chronicle of humanity. History is often told through great hunts, fearless warriors, and inventions that changed the world. But what if one of the most frequently repeated stories about prehistoric life isn't entirely true? As archaeology enters the age of DNA, the role of women in the distant past is beginning to emerge in a way that looks very different from what we have long imagined. Everything began to change as biological analysis became increasingly precise. In 2020, a study published in Science Advances revealed findings from the Willamaya Pachcha archaeological site in Peru, where a roughly 9,000-year-old burial contained a complete set of large game hunting tools. For many years, the individual buried there had been assumed to be a man. However, protein analysis from tooth enamel and examination of the skeletal structure confirmed that the remains belonged to a young woman. When the researchers expanded their dataset to include hundreds of skeletons from archaeological sites across the Americas, they estimated that roughly 30 to 50% of the individuals buried with large game hunting tools may have been women. That pattern was further reinforced by modern anthropological research. A 2023 review covering 63 hunter-gatherer societies found that 79% of those communities documented women participating in hunting in one form or another. In some groups, they hunted small animals. In others, they joined the entire hunting party in pursuing large prey, using bows, spears, or traps, and sometimes even bringing young children with them. Discoveries involving Neanderthals tell a remarkably similar story. Analyses of carbon and nitrogen isotopes preserved in their bones show that men and women had nearly identical diets, both relying heavily on the meat of large animals. Many female skeletons also bear healed fractures in the shoulders, arms, or ribs, suggesting they regularly took part in physically demanding work or faced dangerous environments. Today, most anthropologists agree that the role of women constantly shifted depending on the human species, the environment, the season, and the stage of life. During pregnancy or while caring for young children, they may have prioritized safer tasks. But at other times, they also hunted, crafted tools, processed food, traveled long distances, and contributed directly to the survival of the entire community. But if prehistoric women were never simply the ones waiting inside the cave, when did that role truly begin? How were the very first mothers able to become pregnant, give birth, and protect their young before there was fire, before sophisticated tools existed, and while predators surrounded them on every side? To answer that, we must travel back in time to the earliest hominins, where humanity's journey into motherhood had only just begun. Around 4.4 million years ago, a female Ardipithecus may have had to leave her resting place before sunrise to search for ripe fruit, young leaves, seeds, roots, insects, or bird eggs. Food sources were unpredictable, while East Africa was gradually transforming from dense forests into open woodlands and grasslands as the climate became increasingly dry. Every foraging trip carried the risk of encountering leopards, ancient hyenas, or crocodiles near water sources. Some of the most important insights into this period come from the famous fossil known as Ardi, discovered in Ethiopia. Artie stood about 4 feet tall, weighed nearly 110 pounds, and possessed a body that seemed to stand between two worlds. Her big toe still splayed outward for gripping tree branches, but her pelvis had already begun adapting for walking upright on the ground. This suggests that Ardipithecus both climbed trees to forage or escape predators, and spent more time moving across the ground than earlier apes. For a pregnant mother, balancing between climbing and walking upright would certainly have been an enormous challenge. Another discovery from Artie has also changed the way we view the society of the earliest hominins. The males had canine teeth that were much smaller than those of modern chimpanzees, and showed little difference from those of females. To paleoanthropologists, this suggests that violent competition between males may have declined. That opens the possibility that individuals were beginning to form more stable social bonds, share food, or help one another care for their young. As human ancestors spent more time walking on two legs and gradually lost body hair through the course of evolution, their infants could no longer cling securely to their mother's fur as many modern primates do. Mothers likely had to use one arm to hold or support their babies while traveling and foraging. Having one arm constantly occupied made climbing trees, gathering food, or defending themselves far more difficult. The need to care for helpless infants may have encouraged cooperation among group members from a very early stage. Perhaps this was one of the first building blocks that laid the foundation for the communal way of life that would later help humanity survive. Looking back, what allowed humanity's first mothers to survive was not superior strength or greater speed than the predators around them. It was resilience, adaptability, and the social bonds that were gradually taking shape. Every child who lived to adulthood was the result of thousands of good decisions accumulated day after day, from choosing where to forage and avoiding predators, to sharing scarce food with one another. Those unnamed mothers laid the very first foundation for humanity's entire evolutionary journey. But around 4 million years ago, nature brought about an even greater turning point. Some of their descendants began walking upright with increasing skill. Their hands were freed, opening the possibility of carrying food, making tools, and caring for their young in ways never before possible. That seemingly simple change permanently transformed pregnancy, childbirth, and the raising of children. The most famous evidence comes from the skeleton known as Lucy, an Australopithecus afarensis individual who lived about 3.2 million years ago in what is now Ethiopia. Lucy stood only about 3 feet 7 inches tall and weighed around 60 pounds, yet her skeleton transformed the way we understand our ancestors. Her pelvis, knees, and feet reveal that she regularly walked upright on two legs, while her long arms and curved fingers show that her climbing ability had not disappeared. Lucy seemed to live between two worlds: the ground, where she searched for food, and the trees, where she escaped predators or rested. It was this remarkable flexibility that allowed mothers to expand their foraging range while still maintaining their chances of survival. Another discovery at Latoli, Tanzania, further strengthens this picture. Preserved in a layer of volcanic ash about 3.66 million years old, scientists found footprints that show a walking pattern strikingly similar to that of modern humans. The heel touched the ground first, weight shifted through the arch of the foot, and the body was pushed forward by the big toe. Instead of relying on all four limbs for movement, she could now carry her child while transporting food or branches, all while scanning farther across the open grasslands for approaching predators. But evolution has never brought only advantages. To make upright walking more efficient, the pelvis gradually changed shape to support body weight more effectively. During the time of Australopithecus, the brain measured only about 400 to 500 cubic centimeters, so childbirth had not yet become a major challenge. Even so, evolution had already introduced a problem that would follow humanity for millions of years. How could our ancestors become increasingly efficient at walking on two legs while still being able to give birth to babies with ever-growing brains? The next major turning point came around 2.6 million years ago, when the first Oldowan stone tools appeared, associated with Homo habilis, and possibly with some later Australopithecus populations as well. They were nothing more than stones chipped to create sharp edges, yet they opened an entirely new way of obtaining food. Before this, an animal carcass abandoned by predators was almost useless because its hide was too thick and its bones too hard. Now, with a sharp stone flake, early humans could slice away the remaining meat and break open bones to reach the marrow, a remarkably valuable source of fat and energy, especially for pregnant or breastfeeding women. Microwear analyses of Oldowan tools also show that they were used not only for processing meat, but also for cutting plants, stripping bark, digging up tubers, and preparing many other kinds of food. This made nutrition more varied and more reliable. More importantly, food began to be shared within communities more often than before. A mother was no longer completely dependent on whatever she could find by herself each day. It was a small step, but one that laid the foundation for the social cooperation that would flourish in later human species. Better nutrition also made it possible for the brain of Homo habilis to grow to approximately 510 to 700 cubic centimeters. The increase was not dramatic, but it marked the beginning of a trend that would shape the entire history of human evolution. Brains would continue to grow larger, children would require more time to mature, and the role of mothers would become increasingly important. If the brain continued to expand, could the mother's body keep pace? Would a pelvis optimized for upright walking still be wide enough to give birth to increasingly intelligent children? The answer would arrive with a new human species about 2 million years ago. They were taller, traveled farther, learned to harness fire, and became the first humans to leave Africa and spread across new lands. Yet that very success pushed mothers into the greatest biological challenge in evolutionary history. Around 1.9 million years ago, Homo erectus appeared and quickly became the first human species to leave Africa. expanding into Western Asia and later East Asia. With long legs, well-balanced bodies, and an ability to walk long distances much like modern humans, they could follow herds of animals across journeys stretching hundreds of miles. But the greatest achievement of Homo erectus was not those remarkable migrations. It unfolded quietly within the bodies of mothers. The brain of this species grew from about 600 cubic centimeters in its early populations to nearly 1,000 to 1,100 cubic centimeters in later ones. A larger brain meant better memory, more sophisticated tool-making, and greater adaptability. Yet with every step forward in brain development, childbirth became more difficult. This is the famous paradox of human evolution. To walk efficiently on two legs, the pelvis had to remain compact enough to conserve energy during movement. But a fetus with an increasingly larger head required a wider birth canal. The timing of birth is determined not only by the size of the pelvis, but also by the mother's ability to supply energy. Once the fetus reaches the maximum level of energy that the mother's body can sustain, pregnancy must come to an end. As a result, human babies are born while their brains are still far from fully developed and continue growing at an extraordinary pace after birth. Unable to sit on their own, unable to find food for themselves, and almost completely dependent on adults throughout the first years of life. Yet it was precisely this helplessness that became humanity's greatest advantage. The brain continued developing within a social environment where children learned language, observed others, imitated behaviors, and accumulated experience. The price mothers paid, however, was enormous. Imagine a Homo erectus woman who had just given birth. She still had to travel with her group in search of water, gather food, or move toward new hunting grounds, while her child needed to be carried constantly and breastfed for years. A mother alone could hardly meet all of those demands. For this reason, many anthropologists believe that by the time of Homo erectus, cooperative childcare among multiple group members, known as alloparenting, had become a crucial survival strategy. For the first time, a child was no longer solely the responsibility of its mother, but became an investment shared by the entire community. Perhaps this was evolution's greatest invention, even more important than stone spears or fire. Another hypothesis also helps explain why humans became so successful: the grandmother hypothesis. Grandmothers could care for grandchildren, share food, and pass on knowledge, allowing their daughters to have more children while increasing the survival chances of the entire family line. Although this hypothesis is still being actively studied, observations of many modern hunter-gatherer societies show that children often have higher survival rates when supported by their maternal grandmothers. It reminds us that a woman's role does not end with childbirth. She also becomes a guardian of knowledge and a bridge through which life continues across generations. During this same period, Homo erectus also achieved significant technological advances, Even more importantly, evidence from Wonderwork Cave in South Africa suggests that they had learned to control fire around 1 million years ago. Cooked food became softer, easier to digest, and allowed the body to extract more energy from the same amount of food. For pregnant or breastfeeding women, that dependable source of energy was especially significant, because every additional calorie helped nourish the developing brain of the next generation. Looking back, the success of Homo erectus did not come simply from traveling farther or thinking more intelligently. It came from turning the task of raising a child into the responsibility of an entire community. When larger brains created a biological burden that seemed almost impossible to overcome, evolution did not choose to make mothers stronger. Instead, it chose to make society more closely connected. Yet a few 100,000 years later, Earth entered prolonged cycles of ice ages. In that frozen world, the lives of mothers would once again be tested by Homo heidelbergensis, Neanderthals, and Denisovans, human species that transformed adaptability into the key to survival on an icy planet. From about 700,000 to 40,000 years ago, the descendants of Homo erectus, including Homo heidelbergensis, Neanderthals, and Denisovans, had to adapt to a planet colder than ever before. For pregnant women, this was an immense biological challenge. Their bodies had to maintain a core temperature of about 98.6 degrees Fahrenheit, while simultaneously nourishing a developing fetus. Modern physiological models estimate that a pregnant Neanderthal woman may have required roughly 4,000 to 5,000 kilocalories per day, significantly more than the energy needs of most modern women. If food supplies were interrupted even briefly, the body would prioritize the mother's survival first, while the fetus would be the first to suffer the consequences. Long periods without sunlight also reduced the body's ability to produce vitamin D, while diets lacking meat or organ meats could easily lead to iron deficiency. Without medicine or hospitals, every pregnancy was truly a battle against nature. What is remarkable is that they did not merely survive. They thrived for hundreds of thousands of years. Archaeological discoveries at Schöningen, Germany, show that Homo heidelbergensis crafted wooden spears nearly 8 feet long, powerful enough to hunt large game. They knew how to maintain fire, build shelters, and organize life within groups. These advances did more than improve hunting efficiency. They created a safer environment for pregnant women and young children. For the first time in evolutionary history, a mother's survival no longer depended entirely on her own strength, but on the coordinated efforts of an entire community. When the Neanderthals emerged, adaptation to extreme cold reached an astonishing level. They possessed short, powerfully built bodies, broad chests, and shorter limbs, features that reduced heat loss in freezing environments. Analyses of carbon and nitrogen isotopes preserved in their bones reveal that male and female Neanderthals shared remarkably similar diets, relying heavily on large animals such as bison, reindeer, and wild horses. This suggests that women were far from isolated from the community's survival activities. Even stronger evidence is preserved within their skeletons themselves. At archaeological sites such as Shanidar in Iraq and Krapina in Croatia, many female Neanderthals bore healed fractures in their ribs, arms, and shoulders that had completely recovered long before they died. This means they had survived severe injuries and continued living for many years afterward. Without long-term food sharing, care, and protection, this would have been almost impossible. European caves have also preserved evidence of tools used to cut, tan, and sew animal hides. These were more than simple garments. For an infant born during a winter below freezing, a carefully prepared hide could mean the difference between life and death. Behind every fur garment lay hours of meticulous work, scraping away fat, softening the hide, and stitching pieces together into insulating layers. If Neanderthals symbolize adaptation to bitter cold, then Denisovans represent another extraordinary achievement. Although scientists have discovered only a handful of Denisovan fossils, ancient DNA reveals that they successfully lived in high-altitude regions above 13,000 feet. This appears to have been made possible by a variant of the EPAS1 gene, which allows the body to use oxygen more efficiently in thin air. Even more remarkable, this genetic variant was passed to the ancestors of modern Tibetans through interbreeding between the two human species. Yet despite their physical strength, extraordinary adaptability, and valuable genetic advantages, Homo heidelbergensis, Neanderthals, and Denisovans all eventually disappeared. Today, most scientists believe there was no single cause. Climate change, populations that had become too small, isolation between groups, and competition with Homo sapiens most likely combined to create a perfect storm. But they did not vanish completely. They left behind genes that still survive in many people today. It was this foundation that paved the way for the emergence of Homo sapiens. Imagine a group of Homo sapiens living around 40,000 years ago. During the earliest years of life, children spent most of their time beside their mothers and older women. As a result, these women did far more than provide food. They passed on the knowledge that allowed the next generation to survive in a world filled with danger. We can still observe this today among hunter-gatherer communities such as the Hadza of Tanzania and the San of southern Africa. Children learn to recognize hundreds of species of plants, roots, and fruits simply by following the adults. They learn which ones can be eaten, which must be cooked, which can be used as medicine, and which must be avoided at all costs. A single mistake could mean the difference between life and death. Every piece of knowledge that was passed down was therefore the result of countless generations of observation and trial. At the same time, archaeology shows that Homo sapiens developed innovations that profoundly transformed everyday life. At Blombos Cave in South Africa and many late Stone Age archaeological sites, scientists have uncovered evidence of bead making, pigment processing, hide tanning, fiber weaving, and, later, bone sewing needles. It is impossible to determine whether any particular tool was made by men or women, but ethnographic studies show that in many hunter-gatherer societies, women often play central roles in food processing, basket making, fiber production, hide sewing, and the creation of everyday tools. Another defining characteristic of Homo sapiens was the ability to build extensive social networks. Archaeologists have discovered seashells, obsidian, and various pigments that had been transported dozens, even hundreds of miles from their original sources. This suggests that human groups did not live in complete isolation, but regularly exchanged materials, gifts, and perhaps even survival knowledge. When one region experienced drought or food shortages, these connections became a safety net that helped communities endure hardship. Through marriages between different groups, women may also have carried knowledge of medicinal plants, edible foods, food preparation techniques, and childcare practices, turning every migration into a pathway for the spread of knowledge. All of this reached its full potential only when combined with language. Although the exact moment when modern language emerged remains unknown, most researchers agree that Homo sapiens developed communication sophisticated enough to recount the past, plan for the future, and pass knowledge to the next generation. Perhaps this was the greatest achievement of Homo sapiens. Throughout that process, women did more than raise children. They safeguarded the storehouse of knowledge that enabled entire societies to survive long before humans ever invented writing. But around 12,000 years ago, as people began settling down, farming crops, and domesticating animals, that very role would face an entirely new challenge. Civilization was being born, but did life truly become better for women? Or were they simply stepping into a different kind of burden? For millions of years before that, hunter-gatherer groups constantly moved in search of food. A mother could hardly carry 2 children who were not yet able to walk over journeys stretching dozens of miles at the same time, so the interval between births typically lasted 3 to 5 years. But once humans settled in permanent communities, food was stored close to where they lived, allowing young children to be fed grain porridge earlier and weaned sooner. In many communities, the interval between births shrank to just 1 or 2 years. The population grew at an unprecedented rate, laying the foundation for the rise of civilization. Yet the price was paid largely by women's bodies. Pregnancy, childbirth, and child-rearing became far more frequent, placing greater strain on their nutrition and health than at any previous stage of human history. Agriculture did more than change the way humans reproduced. It transformed the human diet itself. During the hunter-gatherer era, people ate a diverse range of foods, including meat, fish, fruits, nuts, roots, and seasonal plants. After the transition to farming, many communities became dependent on just a few staple crops such as wheat, barley, or millet. Analyses of thousands of Neolithic skeletons from Western Asia, Europe, and the Americas reveal that average height declined. Tooth decay became more common, and signs of iron deficiency anemia appeared far more frequently. For pregnant women, iron deficiency not only weakened the body but also directly affected fetal development. This presents a striking paradox. Humanity was producing more food than ever before, yet the nutritional quality of many communities actually declined. Another discovery is even more surprising. In 2017, researchers at the University of Cambridge compared the arm bones of women who lived around 7,000 years ago with those of modern women. The results showed that their bones were 11 to 16% stronger than even those of today's elite rowers. This did not mean they were stronger because of athletic training. Rather, it reflected the countless hours they spent every day grinding grain with stone querns, carrying water, working in the fields, weaving textiles, and preparing food. Civilization did not make women's work easier. It merely changed the nature of their labor. Long hunting expeditions were replaced by repetitive tasks performed from morning until night, day after day. Studies in paleopathology show that after the rise of agriculture, infectious diseases and illnesses associated with poor sanitation became much more widespread. For pregnant women and newborns, these threats were especially dangerous. Their enemies were no longer limited to predators or harsh winters, but now included invisible organisms that could not be seen with the naked eye. The agricultural revolution also brought positive changes. Women remained at the center of the household, not only raising children, but also managing food supplies, preserving essential skills, and passing knowledge on to future generations. It was these quiet, often overlooked responsibilities that enabled agricultural communities to flourish sustainably for thousands of years. So, was agriculture truly better for women? It created a stable food supply, fueled a population explosion, and paved the way for civilization, but it also brought greater reproductive demands, heavier labor, and more disease. Evolution has never offered humanity a perfect life. It has simply continued to replace one set of challenges with another. If you had the choice, would you rather live as a woman in a hunter-gatherer band, free, yet surrounded by uncertainty, or in a more stable farming village where life was more secure, but the burdens were greater? Perhaps that question reveals the most important lesson of this entire journey. What allowed humanity to survive and build civilization was not agriculture, tools, or cities alone, but the enduring ability of women to adapt to every change in nature and society. And with that, we arrive at the final question of this nearly 7 million year journey. Without the mothers who quietly endured every one of those challenges, would humanity ever have become the dominant species on Earth that it is today? The story of human evolution was shaped not only by hunts and inventions, but also by the millions of years during which prehistoric women sustained and nurtured life. From the earliest human species to Homo sapiens, they did far more than ensure the survival of the next generation. They played a direct role in shaping both the biological and social evolution of humanity. Our existence today stands as evidence of the extraordinary resilience of both women and men, who together carried humanity through Earth's greatest hardships and toward the dawn of civilization. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.